Our solar system formed out of a massive disk of gas and dust some 4.5 billion years ago. Better understanding this system and the wider universe is a major mission of NASA. Observation and supercomputer simulations work hand in hand to probe nature's workings, not just in the present, but also to test theories about their past and future. Of all the solar system bodies, the sun naturally dominates. It sustains life on Earth by bringing light and warmth. The sun can be a destructive force. At times, it streams highly energetic particles into our atmosphere, knocking out satellites and power distribution stations. Those particles are accelerated by changes in the sun's magnetic field. What then creates the magnetic field? One answer is turbulent convection. Like soup boiling on a stove, gas at the sun's surface is heated from the bottom and cooled at the top. In this simulation, brighter colors trace hot regions which rise, darker colors trace cool regions which sink. Since the gas conducts electricity, these motions produce magnetic fields. The sinking cool gas concentrates the magnetic fields into small elements, colored red. Areas left bare of magnetic field are colored blue. About 100 kilometers wide, the magnetic elements were only recently found by high-resolution observations. Thousands of these elements contribute significantly to the sun's overall magnetic activity. When a large bundle of magnetic field lines breaks through the sun's surface, a sunspot can form. Sometimes a smaller spot will emerge nearby, creating a magnetically complex region where particles are energized and then violently expelled. Supercomputer models show that rearranging magnetic field lines enables this process. The magnetic field at the sun's surface is coded in color ranging from blue for strong fields pointing into the sun to red for strong fields pointing out of the sun. The white lines represent magnetic field lines. The underlying magnetic field is stretched, forcing oppositely directed field lines together so that they break apart and reconnect. Reconnection causes many lines to open into space, clearing a pathway for the energized particles to escape. Leaving the sun, Earth soon comes into view. NASA science probes the interrelating oceans, land, and atmosphere. Among Earth's most powerful phenomena is El Niño, a periodic warming of the eastern Pacific Ocean. Satellite, ship, and buoy observations show the 1997 to 1998 event as the strongest on record. Its impact surpassed only by the seasons, El Niño globally changes precipitation and temperature patterns, often with grim results. Visualizing how 3 key data sets differ from normal conditions reveals the event's magnitude and gives new insights into how the ocean and atmosphere couple to produce El Niño. First, we look at sea surface height. The gray sheet rises and dips as much as 30 centimeters from normal. Next, we map sea surface temperature. Red is 5 degrees Celsius above normal and blue 5 degrees below normal. Finally, black arrows are added to mark sea surface winds. A weakening of the trade winds in the far western Pacific fuels an eastward moving wave. Sea level is raised as the windswept wave progresses. The wave's arrival at the South American coast reduces the normal upwelling of cold water and warms the surface by as much as 5 degrees Celsius. Intense atmospheric convection associated with equatorial ocean warming causes local winds to converge, abating the trade wind strength and extending the warm pool of water into the eastern Pacific. One result of this El Niño was an increase in tropical cyclones. Cyclone Susan barreled through the South Pacific in early January 1998. The Tropical Rainfall Measuring Mission satellite, launched in November 1997, observed rain height and coverage. Red coloring indicates rainfall exceeding 5 centimeters per hour. Another satellite, the August 1997 launch SeaWIFS, took this startling true-to-life view of the Gulf of Mexico and North America's east coast in early April 1998. As we begin, the Mississippi River snakes through the left portion of the scene, emptying into the Gulf at New Orleans. Moving eastward, Tampa-St. Petersburg comes into view. Green-colored water marks sediment, plankton, and sea bottom reflection in shallow areas. The Florida Keys soon appear. They are separated from the shallow waters of the Bahama Banks by a deep water channel. Here's where the Gulf Stream gets funneled northward. The cloud bank mirrors the western edge of the warm Gulf Stream. Along the coast, several southeastern rivers spill into the Atlantic. Nearing Cape Hatteras, the jagged edges of the Gulf Stream are clearly apparent. Next, we pass the Chesapeake Bay, Long Island, and Cape Cod. The Great Lakes are in the background. Snow dots and covers the landscape of northern New England and Canada. Passing Nova Scotia, we see the St. Lawrence River, a major entry point for ships. Stepping back from the coast, we consider the northern Atlantic Ocean as a whole. This high-resolution model follows ocean current velocity over 5 years. Velocity ranges from 30 centimeters per second shown in blue to 200 centimeters per second shown in red. The model realistically separates the Gulf Stream from the Florida coast. Such a small feature had not unfolded in lower resolution models. As the Gulf Stream flows eastward, it creates eddies narrower than 100 kilometers. These currents contain most of the ocean's kinetic energy, and a model must resolve them to correctly produce ocean heat transport. The influence humans have had on their planet can be seen from space. Viewing Earth at night, we see lights of countless villages, towns, and cities. Major urban population centers shown in white are prominent sources of light. Fires from slash-and-burn farming and the burn-off of natural gas and oil fields are shown in red and yellow. This perspective unveils the breadth of human activity on Earth. It spans the globe. An ongoing global effort is the International Space Station. Like any spacecraft in orbit, the people and objects on board will be in free fall. This state of near weightlessness is called microgravity. Matter behaves differently in a microgravity environment. Most critical is how gases and liquids will flow through the station's life support and safety systems. Many believe the station will also be a platform for microgravity experiments, such as manufacturing computer chips and assembling protein crystals for drugs. Simulations can help scientists understand how heated or cooled fluids behave in microgravity. Computationally reducing gravity, we find that temperature variation on the fluid surface becomes dominant and causes the fluid to move. A few degrees variation can lead to significant motion. Colors trace the temperatures, which increase with reddening. The ribbons display the path of fluid motion. Particularly abundant natural space objects are asteroids. Hundreds of thousands cross Earth's orbit around the Sun. Larger than average, this is the asteroid Castalia in a cutaway view. It is being hit by a house-sized rock traveling at 5 kilometers per second. The scattering white dots are fragments from the smaller rock. Researchers modeled Castalia as a peanut-shaped solid rock 1.6 kilometers long and 0.8 kilometers wide. Fractures appear throughout the asteroid, with the greatest damage shown in red. Lasting merely a second, the collision approximates the force of the Hiroshima atomic bomb. Using nuclear weapons has been proposed for breaking up or at least diverting asteroids headed towards Earth. The simulations show that such an impact will fracture a solid asteroid, but later gravity will reassemble the pieces. From Castalia, we trek to our next planetary neighbor, Mars. The true global geography of the planet first emerged with comprehensive maps from Mariner 9 and Viking. Valles Marineris is an enormous system of canyons nearly 5,000 kilometers long and up to 9 kilometers deep, probably initiated by the crust being pulled apart in a great fracture. The volcanoes of Mars are of a size found nowhere else in the solar system. Olympus Mons covers an area the size of Colorado and towers over the adjoining countryside nearly 3 times as high as Mount Everest. Over the ages, thousands of eruptions have built up a lava cliff surrounding Olympus. Traces of these eruptions cover the flanks of the mountain. Martian surface is now drier than the Sahara, but there is extensive evidence that this was not always the case. The Ophir Chasma is thought to contain the sediments of an ancient lake. To the northeast on the vast plain of the Ares Vallis, ancient erosional channels tell of massive flooding, perhaps from subsurface permafrost melted by volcanic heat or meteor impacts. The size and scope of these channels suggest one-time flow rates thousands of times greater than the Amazon River. The Viking landers found no chemical traces of life. However, in 1996, studies of a meteorite found in Antarctica and of known Mars origin showed microscopic structures resembling the fossils of ancient bacteria. Today, more than 2 decades after Viking, NASA continues to return to Mars with new lander and orbiter missions. They are designed to greatly enhance our knowledge of Mars and renew the search for life. Well beyond our solar neighborhood are systems of orbiting neutron stars. These binary systems are born when the cores of 2 old stars collapse in supernova explosions. Neutron stars have the mass of our Sun, but are the size of a city, so dense that boundaries between atoms disappear. In this simulation, the translucent spheres are the neutron stars. The flat circles are a cross-section through the equators. Colors map matter density, which increases as colors move from yellow to blue to red. Einstein's theory of general relativity predicts that the orbit shrinks from ripples of spacetime called gravitational waves. After about 1 billion years, the 2 neutron stars closely circle each other at 60,000 revolutions per minute. The stars finally merge in a few milliseconds, sending out a burst of gravitational waves. New supercomputer models taking relativity fully into account will be able to predict the gravitational wave signal. With that, scientists can detect the possible formation of the more massive black holes and perhaps better estimate the expansion rate of the universe.